Look at this swarm of information. When we try to locate a single target inside a massive, unorganized system, the hardware faces an immediate bottleneck. If you search element by element, what computer scientists call a linear search, you are forced to check every single item until you find a match. That works for 100 records. Scale that to 1 billion, and the computation time becomes paralyzing. The solution to this scaling problem is a divide-and-conquer strategy known as binary search. It moves away from the one-by-one inspection of linear search toward a system of strategic elimination. But to deploy it, we must impose order. As you see here, the algorithm requires a strict prerequisite. The data must be sorted or monotonic. Pre-sorting the data is the architectural cost we pay up front. We accept that initial expense because it creates a foundation for search speeds that remain fast even as the dataset grows by orders of magnitude. The mechanics of the algorithm lie in a single deterministic rule. With every iteration, it eliminates exactly 50% of the remaining search space. This graph illustrates the impact of that rule. The steep line represents linear growth, where processing time increases directly with the size of the data. The flattening curve below it is logarithmic growth, the defining signature of binary search. In mathematics, a base 2 logarithm describes how many times you can divide a number in half before you reach 1. That division is exactly what our algorithm is executing. This creates a strict ceiling on our execution time. The absolute maximum number of steps required to find any target is capped at the floor of the base 2 logarithm of n plus 1. Because of this mathematical limit, expanding your dataset from 1,000 elements to 1,000,000 elements only requires about 10 extra steps. You completely decouple the size of your database from the speed of your retrieval. Let's examine the environment. On the left side of this split screen, we have an array of 10 sorted integers, indexed 0 through 9. Our target value is 23. We begin by establishing boundaries. We pin a low pointer to index 0 and a high pointer to the final index, 9. Next, we locate the center. The standard calculation is low plus high minus low divided by 2. You might wonder why we don't simply add the low and high indices together and divide by 2. In massive datasets, this can exceed the hardware's maximum integer limit, causing an overflow error. This specific subtraction method guarantees absolute system safety. Running the math on our initial boundaries drops our midpointer exactly at index form, which holds the value 16. We execute the first algorithmic comparison, evaluating our target, 23, against our midpoint value, 16. 23 is greater than 16. Because the array is sorted, we know with absolute certainty that our target cannot exist at index 4 or anywhere below it. We discard the lower half of the array. It is rendered mathematically irrelevant in a single operation. Our boundaries update. The low pointer shifts up to the midpoint plus 1, landing on index 5. The core loop now restarts, strictly confined within this new narrowed search space. We recalculate the center. Applying our formula to the new boundaries places the next midpoint at index 7, holding the value 56. We execute the second comparison, the target 23 against 56. 23 is less than 56. The entire upper half is discarded. The high pointer shifts down to the midpoint minus 1, resting at index 6. We run the division one last time. Between indices 5 and 6, the integer math resolves our new midpoint to index 5. We evaluate the value at index 5. It is 23. The match is verified. A process that would have taken 6 individual checks using a linear search was accomplished here in exactly 3 operations. Abstract pointer logic is elegant, but to execute on hardware, it must be translated into syntax. In the right panel, we have the iterative implementation. It relies on a standard while loop. The loop requires a strict termination protocol. It continues to run only while the low pointer remains less than or equal to the high pointer. Inside the loop, the pointers mutate based on our comparisons, reassigning the boundaries to mid plus 1 or mid minus 1 to shrink the window. The primary architectural alternative is recursion, where the search function calls itself. Recursion requires a base case to prevent an infinite loop. If the low pointer crosses the high pointer, the function terminates. Rather than mutating variables, recursive architecture preserves state. It passes the updated boundaries directly into a fresh function call. At the hardware level, evaluating these if-else conditions forces the CPU's branch predictor to guess which execution path the code will take next. Because binary search relies heavily on the specific data being evaluated, you might expect frequent mispredictions. However, the logic is so concise that modern compilers express the instructions as conditional moves rather than true branches, maintaining hardware efficiency. Both designs are viable. The iterative architecture is structurally safer for constrained memory limits, while the recursive architecture offers cleaner state isolation. This table outlines formal time complexity bounds for the algorithm. The best-case scenario is an O of 1, or constant time execution. This occurs when the target matches the exact midpoint on the very first calculation. The worst case is O of logN. This boundary is hit when the target lies at the deepest level of the search tree, or is missing from the data entirely. When we audit space complexity, the structural differences matter. The iterative approach operates in O of 1 auxiliary space, while recursion demands O of logN space. That logarithmic space footprint is generated entirely by the overhead of the recursive call stack. For engineers working in embedded systems or memory-constrained environments, the iterative approach is superior. The utility of this logic extends far beyond flat arrays. Look at this schematic of a B tree. The exact same halving protocol provides the mathematical backbone for modern database indexing. B trees organize massive sets of data into nodes, allowing an operating system to execute rapid, targeted lookups across physical hard disks and file systems. We also rely on this architecture in version control and automated debugging. Tools like Git Bisect run a binary search across a project's timeline. The tool halves the commit history repeatedly, isolating the exact historical moment a bug was introduced into the codebase. There are physical hardware limitations to consider. Searching an array sized exactly to a power of 2 can cause cache collisions in the CPU, known as TLP thrashing. Engineers prevent this by offsetting the midpoint calculation, dividing the search space slightly off-center. Binary search provides a definitive template for divide-and-conquer computational efficiency. The logic proves that finding targets at scale is less about the items you check and more about the millions you safely ignore.